Hello. Today our lecture topic is that imperfections in structure of materials. In our last lectures we have already discussed about the atomic bonding and the crystal structure of different materials. So, before going to start, just let us know what is the importance of imperfections, because sometimes it is required for getting the material properties or maybe the betterment of the material properties. So, the properties of some materials are profoundly influenced by the presence of the imperfections. Yes, of course, sometimes we desire that imperfections should be there, so that we can modify the materials or maybe we can enhance some kind of mechanical properties. To have a knowledge about the types of imperfections that exist and the roles they play in affecting the behavior of materials. So, the discovery of the imperfections in an otherwise ideally in a perfect crystal is one of the most fascinating aspects of solid state science. So, say if I give an example, of brass. So, brass is made of the copper and the zinc. So, if we compare the properties of the brass in compare to the copper, we can found that the brass properties are better than the pure copper. So, now we have to know that what is imperfections. So, an ideally perfect crystal in one which has some unit cells and contains some lattice point throughout the crystals, already we have read these points. Term imperfections, or maybe sometimes we are calling it as a defect, is generally used to describe the any deviations, means any kind of little bit deviations of the ideally perfect crystals, means there is some problems in the crystal structure from the periodic arrangements of its constituents. Defects can exist in any all solid materials. So, there are some basic factors generally which affecting the properties of materials. So, first one is the atomic structure and the interatomic bonding. It is enough to know about the bonding and structure of materials to estimate its macro properties, and another one is defects. So, defects to have a significant impact on the properties of a material. So, first we have to know what is crystalline defects. So, generally the crystalline defects means a lattice irregularity having one or more of its dimensions on the order of an atomic diameter. So, generally a crystal or maybe material is having a specific crystal structure. In that crystal structure we can see some kind of vacancy, some kind of defects. So, these all are known as the crystalline defects of that particular material. Defects in the crystalline structure can have tremendous effect on material behavior, because we can change or maybe substitute some host atoms, or maybe we can put some kind of new atoms inside that host atoms. Like this way we can change the material properties. Physical, electrical, magnetic and the optical properties of crystalline materials can be modified by controlling the imperfections in their lattice structure. For ease of their characterizations, defects are classified on the basis of their geometry, maybe types, which is realistic as defects are disrupted region in a volume of solids. So, from this image we can see that there are so many types of defects like vacancy, like dislocations, then some kind of impurity like substitution impurity or maybe that interstitial impurity, some kind of twin boundary problem, some kind of grain boundary or maybe the stacking fault. So, there are so many types of defects which we are going to discuss one by one in the subsequent slide. So, first we have to know what is the broad classifications of defects based on the dimensionality. So, defects, if we divide it into different or maybe rather I can say into 5 types. First one is called the point defects or maybe the 0D defects like vacancy, self interstitial and the impurity. If we talk about the 1D defects or maybe it is known as line defects also, like edge dislocations, screw dislocations and the mixed dislocations. If we talk about the surface defects like 2D, 2 dimensional in nature, that is external surfaces, grain boundaries and the twin boundaries. and when we are talking about the volume defects, which is 3D in nature, or maybe sometimes it is called the 3D defects, is called the precipitates, dispersants, inclusions and pores, and the last one is known as the atomic vibrations. So, first, what is point defects? So, point defects means it is a imperfect point like regions in the crystals. So, a single point type of defects in the crystal structure. Typical size is about 1 to 2 atomic diameters, also called as the 0 dimensional defects. So, there are several types of point defects like vacancy, impurity and the self interstitial. So, what is vacancy? So, vacancy is the absence of an atom from its regular atomic site. So, from this particular image you can see that in this particular gap some atom should be present over there, but it is not. So, some vacant site has been created, that is known as the vacancy. All crystalline solid contains vacancies, occurs due to imperfect packing during the crystallizations. This result in decrease in density of the substance. Yes, of course, because generally the crystal structure it is very closely packed. If there is gap in between that, automatically the density will decrease. So, what is the necessity of the existence of vacancies? So, generally it can be proved by the principle of thermodynamics. Generally the presence of vacancies increase the entropy or maybe the randomness of the crystal. As I told already, when there is no vacancy the atoms are very closely packed, but when there is any vacancy or maybe has been any gaps has been generated, so automatically the atom will try to move in between those gaps. So, equilibrium number of vacancies, which is denoted by the NV, for a given quantity of material is given by n exponential of minus QV by KT, where n is the total number of atomic sites, QV is the energy required for formations of the vacancy, T is the absolute temperature. So, if at the time of calculations of the equilibrium number of vacancies, if our temperature is in degree centigrade, we have to convert it into Kelvin, and K is known as the Boltzmann constant. So, what is the value of that Boltzmann constant? So, generally if the energy is in joule, so automatically the value of the Boltzmann constant will be 1.38 into 10 to the power minus 23 joule per atom Kelvin, and if the energy is into the electron volt, then the value will be 8.62 into 10 to the power minus 5 electron volt per atom Kelvin. So, the number of vacancies increases exponentially with temperature. For most metals, the fraction of vacancies just below the melting temperature is on the order of 10 to the power minus 4. Now, we are going to discuss about the self interstitial. So, if the matrix atom occupies its own interstitial site, because from the name itself we can understand that that has been done or maybe the created by the host atom itself, the defect is called the self interstitial. This defect increases the density of the substance. Yes, of course, because there is no vacant place is left. In metals, a self interstitial introduces relatively large distortions in the surrounding lattice strain, since the atom is substantially larger than the interstitial site. So, in this particular case you can see that atom has been self interstitial, has been means taken place or maybe has been inserted or maybe has taken the place in between the atoms, and then it is giving a pressure or maybe the strains to the surrounding atoms. Formation of this defect is not highly probable. It exists in very small concentrations which are significantly lower than for vacancies. Now, we are going to discuss about the impurity. Impurity atoms are added intentionally in alloys to impart specific characteristics of the materials. Yes, of course, sometimes by knowingly or maybe sometimes by unknowingly we are adding the impurities to the systems or maybe to the matrix or maybe to the alloys or maybe composites. Sometimes we are adding the materials by knowing variations or maybe by knowing compositions to increase certain properties. Sometimes while we are preparing the composites, we are adding so many constituents, through that constituents also some impurity unknowingly it is coming into the system. Alloying is used in metals to improve the mechanical strength and corrosion resistance. So, if I give an example of the sterling silver, it is made of 92.5% silver with 7.5% copper alloy. If I give an example of the gold ornaments, generally we are not using the 100% gold over there, because otherwise it will not be malleable. To make the gold into a malleable format, we are adding some kind of materials into it so that it can be malleable. Alloying with copper enhances the mechanical strength without depreciating the corrosion resistance in case of the sterling silver. Additions of impurity atoms to a metal will result in the formation of a solid solutions or maybe new second phase. So, generally in a systems I am having the host atom, and then from outside I am adding another third party atom. So, a solid solution forms when the solid atoms are added to the host material. So, here solid atoms is the third party materials. The crystal structure is maintained and no new structures are formed. So, generally there are two ways: solid are element present in a minor concentrations. So, whatever the impurity I am adding, that concentrations or maybe quantity is very less. Another one, solvent or host atoms, of course their numbers are in very large or maybe the greatest amount. So, a solid solutions is also compositionally homogeneous. So, solid solution formations generally it depends on three characteristics. One is called the kinds of impurity, then concentrations and the temperature of the alloy. Right hand side you can see that when we are talking about the solid solution of the zinc in copper, so you can see they are perfectly in order, but when we are talking about the compounds, the atoms are very closely packed, but they are not in order. So, that is the basic difference in between the solid solutions and the compound. Now, if we see about the impurity, there are two types of impurity. One is called the substitutional, another is called the interstitial. So, from the name itself, for substitutional we can understand that it is substituting some atom. So, solute or impurity atoms replace or substitute for host atoms. So, simple, there is some host atoms, but the impurity atoms it is substituting the host atoms inside the crystal structure. And when you are talking about the interstitial, so impurity atoms fill voids or interstitials among the host atoms. So, here you can see there is certain gap, in between that gap the impurity atom is taking place or maybe it is taking that area. Interstitial positions are small for metallic materials that have high atomic packing factors, because they are very closely packed. So, in between the atoms the gaps are or maybe the places are very small. Atomic diameter of an interstitial impurity is smaller than the host atoms. Solid solutions are also possible for ceramic materials. Now, what are the factors which determines the degree of dissolving of solute in solvent atoms are as follows. First is called the atomic size factor. The difference in atomic radii between the two atoms types is less than about 15%. Otherwise, the solute atoms will create substantial lattice distortions and a new phase will form, but this is only valid for the substitutional impurity, not the interstitial one. Then crystal structure, the crystal structure for metals of both atoms types must be the same. Then electronegativity, the more electropositive one element and more electronegative the other, the greater is the likelihood that they will form an intermetallic compound instead of a substitutional solid solutions. Then valences, metal will have more tendency to dissolve another metal of higher valency than one of a lower valency. So, these all are the important parameters. Suppose when we are trying to make any kind of new composites or maybe trying to do the doping or maybe some kind of insertions of the impurities into some base metals. So, generally these all are the factors which we need to look, and then based on that we have to choose the proper materials and or maybe the impurities, and we have to insert them into the host material. So, now what is the specifications of the compositions? So, what is compositions? So, compositions or concentrations is the relative content of a specific element or constituent in an alloy. There are two most common ways to specify the compositions. One is called the weight percent, another one is called the atom percent. So, what is weight percent? Basis for weight percent is the weight of a particular element relative to the total alloy weight. Computation of weight percent for a 2 element alloy is given as C1 is equal to M1 by M1 plus M2 into 100, where M1 is for the one element and M2 for the second element. And now, when we are talking about the atom percent, so the basis for atom percent calculations is the number of moles of an element in relation to the total moles of the elements in the alloy itself. So, number of moles in some specified mass of a hypothetical element 1 may be computed as N M1 is equal to M1 by A1. So, here A1 and M1 denotes the mass in grams and atomic weight for element 1. So, computation of atom percent for a 2 element alloy is given as C1 prime is equal to NM1 by NM1 plus NM2 into 100. So, if we are going to calculate the percentage weight percentage of different element or maybe the atom percent of different element. So, we can get like C1 prime is equal to C1 A2 by C1 A2 plus C2 A1 into 100, and C1 is equal to C1 prime into A1 by C1 prime A2 plus C2 prime A2 into 100. But any of the cases C1 plus C2, because total composition constituent is 100. So, of course, C1 plus C2 will be 100 or maybe C1 prime plus C2 prime will be 100. Now, convert the concentrations from weight percent to mass of one component per unit volume of material. So, from units of weight percent to the kg per meter cube, the conversions is C1 double prime is equal to C1 by rho 1 plus C2 by rho 2 into 1000, and C2 double prime is equal to C2 by C1 by rho 1 plus C2 by rho 2 into 1000. So, for density rho in units of gram per centimeter cube, these expressions yield C1 double prime and C2 double prime in kg per meter cube. So, like this way we can calculate the average, means rho average, density average and the atomic weight average of that particular atoms or maybe the constituents. Now, we are going to discuss about the line defects. So, generally from the name itself you can understand the defects will takes place along a line or maybe it looks like a line inside the crystal structure. So, line imperfections are also called the linear dislocations. They are abrupt changes in the regular ordering of atoms along a line or maybe the dislocation line in the solids, occur in high densities and strongly influence the mechanical properties of materials. It is characterized by the Burgers vector. The name of the scientist is Burgers, who has invented this one. So, what is the Burgers vector? Burgers vector tell us that whose directions and magnitude can be determined by constructing a loop around the disrupted region and noticing the extra interatomic spacing needed to close the loop. Dislocations occur when an extra incomplete plane is inserted. The dislocation line is at the end of the plane itself. So, this can be proved by the transmission electron microscope image of the titanium alloy, where we can find that there is some black color, dark black color lines are present, which is known as the dislocations of that particular alloy. So, dislocations can be observed in crystalline materials using the electron microscopy techniques like HR-TEM or maybe the TEM or maybe the scanning electron microscopy or maybe that fine FESEM. They are involved in the plastic deformations of crystalline materials, metals, polymers and the ceramics. Now, there are several types of that linear dislocations. So, first is called the edge dislocations. So, what is edge dislocations? The dislocations is called a line defect because the locus of defective point produced in the lattice by the dislocation lie along a line itself. So, here you can see the dislocation, it is in a line and it has been shifted. So, anywhere it can be presented inside the material. The edge defect can be easily visualized as an extra half plane of atoms inserted in a crystal structure. So, extra half plane you can see that red in color and it is shifting. Barger vector, which is denoted by the small b, is perpendicular to dislocations line. So, in this particular case, so this is your line vector and Barger vector is here, which is exactly the perpendicular to that line vector. So, now second is the screw dislocations. So, Barger vectors in this case is parallel to the dislocations line. So, in this case the dislocation lines, if you see the dislocations line over here and Barger vectors is here. So, almost it is parallel to the dislocations line. It is like a spiral ramp with an imperfection line down its axis. So, in this case you can see that two surface it is like. So, it is a screwing type of arrangement is taking place. So, first a plane is created and then after that it is divided into two parts. The motion of a screw dislocations is also called a result of shear stress. How? The motion is perpendicular to direction of stress rather than parallel edge. Net plastic deformation of both edge and screw dislocations is same. So, symbol, by this symbol generally it is used to designate a screw dislocation. Now, the third one is called the mixed dislocations, where we can found the both. So, found in crystalline materials, they are neither pure edge nor pure screw, but exhibit components of both types over there. The character of a dislocations may change along its line, however, the direction of Barger vector remains the same. So, in a mixed dislocation showing a screw dislocation at the front of the crystal gradually changing to an edge dislocation at the side of the crystal itself. So, from screw it is starting and then at the last it is showing the edge dislocations over there. So, the line directions of the mixed dislocation is parallel to the Barger vector of the screw dislocations and perpendicular to the edge dislocation. Next, energy of dislocations. So, dislocations have distortion energy, energy per unit length associated with them. So, generally edge dislocations which is in compressives and the tensile stresses, and screw dislocations is mainly for the shear strains. So, energy of a dislocations per unit length E is more or less equal to half GB square. So, what is G? G is the shear modulus and B is the Barger vector. So, there are two types of generally energy for the dislocations, one is called the elastic energy, another one is called the non-elastic energy, which is more or less E divided by 10. So, summary of the dislocations if we go through, which I have already told you. So, if we go for the edge, it is perpendicular because the dislocations line and the Barger vector are the perpendicular. Slip directions is parallel to Barger vector, direction of dislocation line movement related to B is parallel, process by which dislocation may leave slip plane is climb, and screw it is parallel, then parallel to B, it is perpendicular in nature, and the process by which the dislocation may leave plane slip is cross slip. Now, we are going to discuss about the surface defects. So, generally also called as the interfacial defects. Surface defects is also sometimes known as interfacial defects. They are boundaries that have two dimensions and normally separate regions of the materials that have different crystal structures and or crystallographic orientations. They refer to the regions of distortions that lie about a surface having thickness of a few atomic diameters, not thermodynamically stable, rather they are metastable imperfections arise from the clustering of line defects into a plane. So, there are several types of interfacial defects are present. So, first one is called the external surfaces, then grain boundaries, then twin boundaries, then stacking faults, and last one is called the phase boundaries. So, what is external surfaces? The environment of an atom at a surface differs from that of an atom in the bulk itself. especially the number of neighbors coordination at surface is less. Thus, the unsaturated bonds of surface atoms gives rise to a surface energy. This results in relaxation, the lattice spacing is decreased or reconstructions crystal structure changes. To reduce the energy, materials tend to minimize if possible the total surface area. Next, grain boundaries. So, grain boundary is a interface between two crystals or maybe the grains of same phase, but different orientations, means that is a one kind of boundary wall in between the two different grains. Reasons for grain boundaries: lower density and different orientations of atoms or maybe the ions, relaxation of atomic positions, often different compositions, that means segregations of the impurities, dopants or maybe the lattice defects, and different properties like charge and mass transport or maybe the dielectric or maybe the optical. So, grain boundaries, in this particular case you can see that there are three types of grain boundaries, grains are present, or rather I can say that grain A, grain B, grain C, and this is known as the grain boundary, because the characteristics of these three grains, the structure or maybe the properties are different. Grain boundaries are several atoms distance wide and there is mismatch of orientation of grains on either side of the boundary itself. Various degrees of crystallographic misalignment between adjacent grains are possible. Boundaries are described in terms of aligned dislocations arrays. Internal surfaces of a single crystal where ideal domains meet with some misalignment results in high and small angle grain boundary. So, there are generally two types of grain boundary, one is called the small angle grain boundary or maybe the low angle grain boundary, another one is called the high angle grain boundary. So, when you are talking about the high angle grain boundary, so in this image you can see that this is known as the high angle grain boundary and this is the small angle grain boundary. How? High angle grain boundary contain large areas of pore fit and have a relatively open structure. So, in this case the angle of misalignment is more. So, that is why it is called the high angle grain boundary, and in this case the angle of misalignment is less. So, that is why it is called the low angle grain boundary. Then high angle grain boundary have high energy, high diffusivity and high mobility, and for the low angle grain boundary, when misalignment is slight on order of few degrees less than 10 degree, means area of misalignment, it is low angle grain boundary. Now, there are grain boundaries that is also for two types, as tilt boundary, another one is called the twist boundary. So, in the tilt boundary you can see that the grain boundary, it has been tilted with some angle, and twisted means there is certain kind of rotations in between the grain boundaries. So, when you are talking about the tilt boundary, it is rotations about an axis in the boundary plane. So, this is the axis and through which the rotation is taking place. They are low grain boundary formed by the edge dislocations, and when you are talking about the twist boundary, so it is rotation about an axis perpendicular to the plane. So, this axis, it is totally perpendicular to the plane itself. They are low grain boundary formed by screw dislocations. Both tilt and twist boundaries are planar surface imperfections in contrast to high angle grain boundaries. For high angle grain boundaries, degree of disorientations is of large range, that is more than 15 degree. Grain boundaries are chemically more reactive because of grain boundary energy. And what is grain boundary energy? Generally it is denoted by the gamma. So, excess free energy associated with the presence of grain boundary with perfect lattice as reference points. It is proportionality constant between the increment in total system energy and increment in area. So, gamma is equal to dG by dA. Now, we are going to discuss about the twin boundaries. So, special type of grain boundary across which there is specific mirror lattice symmetry. So, in this case this is known as the twin plane of that boundary. So, mirror like image is taking place into the opposite side. Twin boundaries occur in pairs such that orientation change introduced by one boundary is restored by the other. Region between the pair of boundaries is called the twinned region. So, mirror image. twins results from atomic displacement due to applied mechanical shear force and also during annealing heat treatment. Twin do not extend beyond a grain boundary. So, twin are of also two types, one is called the annealing twins, another one is called the deformation twins. So, what is annealing twins? Formed during process of crystallizations found in metals that have FCC, face centered cubic crystal structure. Deformation twins found in the body centered cubic and HCP metals and formed during the plastic deformation. Next is called the stacking faults. So, formed by fault in the stacking sequence of atomic planes in the crystal itself, found in FCC metals when there is an interruptions in ABC, ABC, ABC and so on stacking sequence of close packed planes. So, here you can see ABC, ABC, then this A is missing, then BC, again ABC, ABC. So, this is known as the stacking faults. So, generally the stacking arrangements of the FCC structure. Then next is called the phase boundaries. Phase boundaries exist in multi-phase materials across which there is a sudden change in physical or chemical characteristics of the materials itself. Then volume defects, it is also called as a 3-dimensional defects or maybe the bulk defects. They are normally introduced during processing and fabrication steps. They manifest themselves macroscopically as pores and cracks. Divided into 4 types of the basis of size of defects and effect they have on properties of the crystal itself. So, types of volume defects, first one is called the precipitates. What is that? Small particles introduced into the crystal matrix by solid state reactions increase the strength of the alloy. Then second one is called the dispersants. So, particles vary from a fraction of a micron in size to 10 to 100 microns. They act as a second phase. The properties of lattice such as mechanical strength, electrical conductivity are some weighted appanage of corresponding properties of dispersant and parent phase. So, that is the mixing of both the phases. Then inclusions, from the name itself you can understand that inclusions means introducing something inside the matrix. So, in this case foreign particles or maybe the large precipitate particles are included. Undesirable constituents in the microstructure, harmful in microelectronic devices. Inclusions are important factors when it comes to gem valuations. So, inclusions inside the diamond. So, some kind of unwanted materials has been inserted into the diamond. In many gemstones such as diamonds, inclusions affects clarity of the stone, diminishes the stone's value. Yes, of course, because it is reducing the cost, because some kind of third party element which is cheaper in nature has been incorporated or maybe it is already present inside the diamond itself. So, cost of the diamond will reduce and the clarity of the stone or maybe the glittering property of that particular stone has been increased. In some stones, star sapphires, inclusion actually increase the value of the stone itself. Inclusions disturbs geometry of device by interfering in manufacturing or alter its electrical properties by introducing the undesirable properties of their own. Then next one is that voids or maybe the pores. So, caused by gases trapped during the solidification or by vacancy condensation in the solid state. Yes, of course, because when we are heating that materials, then the materials is changing its phase from solid to liquid, and then when it is liquid, the liquid metal is having the affinity that it can absorb the moisture or maybe the oxygen or maybe that hydrogen gas from the environment itself, and that will be trapped inside the molten metal, and then at the time of solidifications that trapped gas, by increasing the volume it will make a crack and it will come out and it will create a hollow space inside it which is known as the pores or maybe the voids. Almost always undesirable defects, decreases mechanical strength and promote the fracture at small loads, affect optical, thermal and mechanical properties. So, in this particular image you can see through that FEACM type of image that void has been cracked or maybe the pores or maybe the cracks has been generated. Then atomic vibrations. So, it occurs at 0 temperature and increase in amplitude with temperature itself. At any given time, each atom in a crystal is vibrating about its lattice positions within the crystal itself. So, from this image you can see that vibrations is taking place inside the crystal structure. So, vibrations displace transiently atoms from their regular lattice side, which destroys the perfect periodicity. Due to that vibrations, some atoms may be shifted from their original place. In a sense, these atomic vibrations may be thought of as imperfections or defects. At room temperature, a typical vibrational frequency of atoms is of the order of 10 to the power 13 vibrations per second, whereas the amplitude is a few thousandths of nanometer. Many properties and process in solids are manifestations of this vibrational atomic motions. What is the examples? Melting occurs once the atomic bonds are overcome by the vigorous vibrations. So, when we are heating that materials, so vibrations have started in between the atoms, due to that the melting occurs of the metal itself. Then we are going to discuss about the imperfections in ceramics. So, generally it includes the point defects and the impurities. So, what is the point defects in ceramics? So, it is non-stoichiometric, refers to change in compositions. Effect of non-stoichiometry is a redistribution of atomic charges to minimize the energy. Charge neutral defects include Frankel defect and the Schottky defect. So, what is Frankel defects? So, involves a cation vacancy and a cation interstitial pair itself. So, the vacancy has been created over here. Cation moves from regular site to the interstitial site. So, from here it has been moved from here to here. And what is Schottky defects? Involves a pair of nearby cations and anions vacancy. So, in this particular zone, both cations and anions has been shifted. Movement of one cation and one anion from the lattice to the external surface. So, that is known as the Schottky defect. So, equilibrium number of both Frankel and Schottky defects increase with and depends on the temperature itself. For Frankel defects, number of cation vacancy or maybe the cation interstitial pair, which is known as the NFR, is given as NFR is equal to n exponential of minus QFR by 2 kT. So, where QFR is energy required for formations of each Frankel defects, n is the total number of lattice sites, K is known as the Boltzmann's or maybe the gas constant, and T is the absolute temperature. And for Schottky defects, the equilibrium number Ns is function of temperature, like Ns is equal to n exponential of minus Qs by 2 kT. Here Q is the energy required for formations of the Schottky defect, n is the total number of lattice site, K is the Boltzmann constant or maybe the gas constant, and T is the absolute temperature. Now, what is the difference between Schottky and the Frankel defects? So, first Schottky defects, it is occurred due to loss of atoms from crystal lattice in stoichiometric units. It decrease in density of the crystal, found in highly ionic compounds with high coordination number and having cations and anions of similar sizes. What is the example? Sodium chloride, NaCl, potassium chloride, KCl, etc. And what is Frankel defect? So, occurs due to missing of ions, means cations, from lattice sites, and these occupy interstitial sites. No effect on the density of the crystal, found in crystal with low coordination number and where the difference in the size of cations and anions is very large. What is the example? Zinc sulphide or maybe the silver chloride, etc. Now, there are impurities also present in the ceramics, that also creates some kind of defects inside the ceramic structure. So, how? Charge balance must be maintained when impurities are present. Example, electronegative impurities that substitute lattice anion or maybe the electropositive substitutional impurities. Impurity can form solid solutions in the ceramic materials. So, in this particular case you can see some kind of substitutional impurity ion is taking place, and in this case the interstitial impurity atom is going inside it. So, impurity atoms can exist at either substitutional or as interstitial solid solutions in ceramics. What is interstitial impurity? An ion goes into interstitial site in an orderly arrangement. For interstitial impurity, ionic radius of the impurity cation must be relatively small in comparison to the anion itself. So, here the interstitial impurity cation is taking place. So, just it is replacing, and when we are talking about the substitutional impurity will substitute for host ion to which it is more similar in electrical sense. To achieve any appreciable solid solubility of substituting impurity atoms, the ionic size and charge must be very nearly the same as those of one of the host atoms. Since there are both anions and cations in ceramics, a substitutional impurity will replace the host ion most similar in terms of charge. Thus, if a substitutional impurity has a different charge than the substituted ion, another defect must be present to balance it out. Yes, of course, because plus and minus, if it is plus plus, then automatically there should be a minus to balance it out. For example, for sodium chloride, Ca2 plus and O2 minus would most likely substituted for sodium Na plus and Cl minus ion respectively. There are two types of impurities are present in this case, substitutional cation and the anion impurities. So, in this case this is without impurity and here Ca2 plus is the impurity. So, in this case the cation vacancy is taking place in this particular case, and when you are talking about the substitutional anion impurity, so like in this case this is without impurity. So, we are having 2 Cl minus which is stacked with the O2 minus. So, here O2 minus is the impurity and the O2 is taking place in this particular zone and anion vacancy is taking place in this particular zone, which is called the substitutional anion impurity. Now, the last one, that is defects in polymer. It is very critical one, it is also very difficult to measure. So, different from ceramics and metals, chains can bond together forming loops and can tie two molecules together. Impurities may include interstitials, side branches or maybe the incorrect blending. Screw dislocations also occur in polymer crystals. Vacancies can occur and alter the chain sequences. Every chain end is considered a defects. So, in this case the screw dislocation is taking place in this particular zone, impurity has been added or maybe has taken place, some chain ends is taking place, vacancy is looks like this or maybe some kind of branching is taking place. Here this one is the non crystalline region that or maybe some kind of dangling chain is taking place. So, these or maybe the loose chain. So, there are several types of defects, but it is very difficult to understand the defects inside the polymer. So, now we have come to the end of this particular lecture. So, we have to summarize. So, in this particular lecture we have discussed about the point, line, surface and volumetric defects in which is exist in all solids. The number and type of defects can be varied and controlled, like example temperature controls the vacancy concentrations. Defects affects the material properties like grain boundaries, control crystal slips. So, it can control the crystal slips also. Defects may be desirable or maybe sometimes it is undesirable. Sometimes it can improve the material properties by inserting some materials or maybe sometimes it may reduce the material properties also. Example, dislocations may be good or bad depending on whether the plastic deformation is desirable or not. Inclusions may be intentions for alloy development, sometimes it is intentionally, sometimes it is unintentionally also. Thank you.